numerical and physical modeling techniques for mountain building and landscape evolution. We will compare computer-based numerical modeling with hands-on analog or physical sandbox-style modeling and see how each reveals the dynamics of active orogenic belts. Two complementary approaches. On the left, numerical modeling solves equations on a computer grid. On the right, analog modeling uses scaled, physical materials in a laboratory sandbox. Each has strengths and limitations, and together they provide powerful insight. First, geodynamic numerical models. Imagine two continental blocks converging, a brittle upper crust riding on a warmer, weaker lower crust. As the blocks collide, a mountain wedge and a deep crustal root develop. Modern codes like aspect, gale, or saw-pale solve force balance and heat transport to predict this evolution over millions of years. A key Himalaya example is channel flow, a weak mid-crustal layer that can be drawn upward by focused erosion at the range front. Next, landscape evolution models. They evolve topography through river incision, hill slope diffusion, and sometimes glacial erosion. Consider a ridge with a river draining to the right. If rock uplift accelerates, channels steepen and erosion increases until a new balance is reached. A common incision rule is the stream power law, E equals K times A to the M times S to the N. Transient features like nick points migrate upstream during adjustment. The frontier is coupling deep tectonics with surface processes and even climate. Tectonic forcing sets uplift. Uplift creates topography. Topography shapes climate and rainfall. Rainfall drives erosion. Erosion unloads the crust and can focus deformation. A feedback loop. A case study is the Eastern Himalayan syntaxis. Focused river incision and heavy orographic rain, coupled with a weak mid-crust, can create a self-reinforcing tectonic aneurysm with very rapid exhumation. Now, analog modeling in the laboratory. A classic sandbox thrust wedge. Sand represents brittle crust, and a weak basal layer simulates a detachment. Pushing a backstop produces a forward-verging wedge that grows toward a critical taper. Erosion at the wedge front can lower the taper and shift where new thrusts initiate. We can also study oblique convergence and extension, strike-slip partitioning, and rift grabens emerge naturally. Modern labs use digital image correlation. A grid or speckles are tracked to quantify strain and slip. A quick comparison. Numerical modeling. Strengths include control and quantitative predictions, long time and large area simulations, and easy data assimilation. Limitations include parameter uncertainty, resolution limits, and computational cost. Analog modeling. Strengths include emergent behaviors, real three-dimensional visualization, and intuitive process insight. Limitations involve scaling challenges, simplified materials, and labor-intensive measurements. Representative studies. Alps analog. A rigid indenter drives a doubly vergent wedge with back thrusts. Digital imaging tracks strain localization, matching field-mapped faults. Himalaya numerical. A viscoplastic crust with a weak detachment coupled to focused monsoon-style erosion reproduces a high plateau and a steep front with rapid exhumation. A practical benefit of numerical models is scenario testing. We can double rainfall or change rock strength and predict how relief, river slope, and erosion respond. Analog models reveal spontaneous structures that guide our interpretations in the field. Together, they cross-validate each other. Summary. Numerical modeling translates ideas into quantitative predictions across deep time and large scales. Analog modeling captures emergent deformation in real materials, providing intuition and discovery. Used together, they help explain why mountain belts like the Himalaya, Andes, and Alps look and evolve the way they do.